Picture this. You're walking across the beach when suddenly you spot a treasure chest. You dig it up, open it, and find 12 golden coins inside. You also find a note saying that one of the coins is a counterfeit and weighs differently than the other pure gold coins. 11 golden coins, you think to yourself. That ought to make me a lot of money. You then walk out of the beach and into a pawn shop. You show the merchant your coins and the note. Fair enough, said the merchant. But I don't want your fake coin, so find it or the deal's off. He then shows you to a scale and says, There, find the fake one, and tell me if it's lighter or heavier than the rest. Also, I don't have a lot of time today, so you can only use the scale 3 times. The question is now, how do you find the counterfeit? This problem is known as a 12-coin puzzle, and it's one of my favorite mathematical puzzles of all time. What I want to do in this video is, of course, solve the riddle, but also try to generalize the problem and talk about important math concepts along the way. So without further ado, let's jump right into it. Before trying to solve this problem, we have to ask ourselves, how does a solution even look like? Well, we can start by labeling all the coins 1 through 12, and because we don't know anything about the setup yet, there are 24 possible options for the odd coin, as each one of the 12 could either be slightly lighter or heavier than the rest. In each one of our weighings, we put 2 equally sized piles of coins against each other. The weight difference is pretty small, so if we put 4 coins on the right and 5 on the left, the latter would be heavier even if the former had a heavy coin. Each weighing has 3 possible outcomes. The scale either tips to the left, tips to the right, or balances. We could visualize this by using trees. The initial state is represented by this node, called the root node. After weighing, it gets 3 children corresponding to the 3 possible outcomes. After weighing again, each of the children gets 3 of their own. After 3 weighings, the experiment ends and we get 27 nodes that don't have their own children, known as leaves. If each possibility for the odd coin is represented by a leaf, and no leaf represents more than one possibility, our solution is valid. Otherwise, we could reach a situation where we weigh the coins 3 times and still don't know which possibility is the correct one. This type of tree, where we partition all possible outcomes based on a set of observations and statements, more generally known as features, is what's known as a decision tree. It's a very powerful tool in data analysis, and it was the inspiration for one of the first AI models all the way back in the 1960s. It worked by training a model that learned which features are the most informative and would categorize our outcomes the best. But what do we really mean when we say one feature is more informative than the other? How do we even quantify information? Well, I'd like to introduce you to... Information theory is the field regarding the measurement, storage, and communication of information. This theory was developed by Claude Shannon, one of the most influential mathematicians and engineers of the 20th century. The standard unit for information is the bit. The same bits as in 8-bit music, and the same bits as in the ones and zeros inside your computer. 1 bit is defined as the amount of information needed to store the answer for a simple yes or no question. For example, let's say that an eye doctor needs to describe their patients for a diagnosis. More specifically, the doctor only cares about 2 traits: whether the patient's eyes are brown or bright, and whether they wear glasses or not. As we're answering 2 yes or no questions, we'd need 2 bits of information to describe each patient. Additionally, as each bit can take 2 values, yes or no, or simply 1 or 0, we get 2 to the 2, or 4 different strings of bits, corresponding to 4 different categories of patients. In this case, where all categories are equally likely, there's a simple relationship between the number of options and the amount of information in bits. If we picked a patient at random, they could belong to each one of the 4 categories, and there are 2 bits of information that are hidden from us. If we ask a question like, does the patient wear glasses, we cut our space of possibilities in half and reveal 1 bit of hidden information. This hidden information also goes by a different name: entropy. You might have heard about it when learning about thermodynamics or when watching 3 Blue 1 Brown's video about Wordle. If you want a deeper explanation about it, go watch that video as well. To understand entropy better, let's say I pick a random number between 1 and 10 and ask you to guess it. You know there are 10 possible options, so using the relationship we found, you calculate there's an entropy of log 10 bits. You could ask me a question, like, is it the number 4? There's a 1 in 10 chance I actually picked the number 4, in which case you'd reduce your possible options to 1 and the entropy to 0. But most likely, 4 isn't the number I picked, in which case you would reduce the options from 10 to 9 and reduce the entropy by just 0.15 bits. If we want to quantify how informative this question was, we simply take the weighted average of the entropy reduction. In our case, there's a 1 in 10 chance we reduced the entropy by 3.32 bits, and a 9 in 10 chance we reduced it by 0.15. So on average, it was reduced by about 0.47 bits. What's really cool about entropy is the way it adds up. If you guessed incorrectly, you could ask another question, like, is your number even? Performing the same calculation, we see the entropy was reduced by about 0.99 bits, a lot more than in the previous question. But what would happen if we ask this question first? Well, we would cut our possibilities exactly in half, reducing the entropy by exactly 1 bit. See what happened here? The prior information from the first question made the second one less informative. In general, prior information can either reduce the entropy or leave it the same, but never increase it. Keep that in mind, it's going to be important later. Now let's stop with the examples and apply what we learned on our puzzle. In the beginning, there's 24 equally likely options. This means there's log 24 bits of information we need to uncover. At the end of the experiment, we want to know exactly what's going on, which means that we have no more hidden information left. Going back to our decision tree, we're going to keep track of a few things when visiting each node. We're going to see which options are possible for that node, and split the 12 coins into 4 sets. The possibly light set, possibly heavy, neutral, and the unknown set, where they could be either of the previous 3. Let's start with the experiment. In the beginning, all 24 options are valid and all coins are in the unknown set. We could choose to weigh coins 1 and 2 against 3 and 4. Again, there are 3 possible outcomes. If the scale tilts to the left, we're left with 4 possibilities for the odd coin. Either 1 is the heavy coin, 2 is the heavy coin, 3 is the light coin, or 4 is the light coin. In that case, coins 1 and 2 move to the heavy set, 3 and 4 move to the light set, and the rest move to the neutral set, because we know for sure they can't be the odd one. However, if the scale balances, we're left with the remaining 16 possibilities. Coins 5 to 12 could either be light or heavy. In that case, coins 1 to 4 move to the neutral set, while coins 5 to 12 remain in the unknown set. We can calculate the entropy after the weighing and see it was reduced by about 1.25 bits. There's also a high-risk, high-reward situation going on here, because the more informative an outcome is, the less likely it is to happen. So if we want to find the most informative weighing, we need to find the sweet spot. As it turns out, we get to this sweet spot when the possibilities are equally divided between all outcomes. That would happen if we weighed 2 groups of 4 against each other. Here's the remaining possibilities for the left child, the middle child, and the right child. This reduces the entropy by log 3 bits. With 3 weighings, we could ideally uncover 3 times as much, which is actually more than we need. The sharp among you might notice that even if we had 13 coins, which have 26 initial options, we'd still be able to uncover more information than needed. Does this mean we could also solve the riddle for 13 coins? Keep that in the back of your head, we'll get to that later in the video. We need to place 4 coins on each band of the scale. It doesn't really matter which ones, so let's weigh coins 1 through 4 against 5 through 8. Moving on to the second one, for each child, we want to find the weighing that reduces its entropy the most. But this time, it's more complicated because we have prior information. Different configurations of coins would differ in loss of entropy, even if they have the same number of coins. In the worst case scenario, if we perform the same weighing again, 1 through 4 against 5 through 8, we learn nothing new and do not reduce our entropy at all. We need to find the configurations that reduce the entropy the most, given our prior information. For this task, this might be the time to stop thinking like a mathematician and start thinking like an engineer. We're going to start with the most general outline, and then work our way down to all the nitty-gritty details. We need to build a tree, where each node corresponds to some state. For now, we only have the root node in its initial state. After that, we choose a weighing. Based on the state and weighing of the root node, we could use some logic to determine the status of the children. We're gonna check all possible weighings and choose the one that reduces entropy the most, ideally by log 3 bits. We then go to each child, choose a weighing for them, calculate the outcomes, and repeat this process until we reach the maximum depth of 3. Looking at the leaves, we could check if the solution is valid or not. Every outcome has to correspond to a leaf, and the leaf's entropy must equal 0. Now let's get to the logic. We start at some node and already have its state. Given a weighing, we want to calculate the states of the children. And now we weigh. If the scale is balanced, we know for sure the odd coin wasn't put on the scale, so we move all those coins to the neutral set. And the coins that weren't weighed remain in their original sets, because we don't learn anything new about them. Things get more interesting when the scale isn't balanced. In this case, we learn something new about each one of the coins. Without any prior information, we know the coins on the heavy side are possibly heavy, the coins on the light side are possibly light, and the coins that weren't weighed are definitely neutral. Since no coin is now unknown, the new unknown set is just the empty set. Now let's take a look at the possibly heavy set. Before weighing, a heavy coin could either be in the heavy set or in the unknown set. In other words, in their union. After weighing, we know that a heavy coin could only be found on the heavy side of the scale. This means that our new heavy set is the intersection between these two. The same goes for the possibly light set. And finally, since the new unknown set is empty, the new neutral set must contain all coins that aren't in the new heavy and light sets. And that's it. That's our logic. We can sum it up using a pseudocode. This isn't actually written in any programming language, it's just a tool we use to describe an algorithm. And here's the pseudocode for the entire algorithm. Now, after we know the recipe for solving this puzzle, all that's left is to put it to the test. First of all, don't be afraid if you don't know how to code. We're going to focus on the logic behind creating a program for solving the puzzle, not on syntax or anything like that. If you are curious about the code, I am going to include a link to my GitHub in the description. When your problem involves trees, it's often very useful to work with recursion. Recursion happens when you define a function using itself. The classic example for this is the factorial function. The factorial of a number n is defined as the product of all integers smaller or equal to n. But you could also define it using a recurrence relation. If we substitute n for n-1, we get a formula for n-1 factorial, which we could sub back in the first equation. We could repeat this process on and on, essentially unraveling our recurrence relation. We do need to be careful and break at some point, otherwise we just keep on going on and on all the way to negative infinity without actually calculating the result. So what we need to do is to introduce an initial condition, also known as a breaking condition. In our case, we know that 1 factorial is 1, so once we reach 1, we can break the recursion and get our final result. And while it's useful for solving mathematical equations, It's also useful for other problems, such as drawing fractals, or in our case, constructing a tree. Anyways, let's get to our code. We describe each node as what's known as a dictionary, which is a way to store a set of values where each one has their name, called a key. In our case, each node has 3 key value pairs. We initialize our tree by creating the root node. We then call the buildTree function, which uses recursion to create our entire tree. Here's how it works. The first few lines are the breaking condition. We want our tree to not exceed the maximum depth, so if we see we have reached it, we return so that we do not create any more children. If the breaking condition isn't met, we move on to creating the children. In this function, we go over all possible weighings and use the logic to find the one that reduces the entropy the most. This function returns the weighing, the state, and the entropies of all children. We then go to each one of the child nodes. If it represents a possible move, we create its children. We keep on going until the entire tree is created. And hopefully, when the buildTree function finishes running, we get a valid solution. Now let's run the code. After a few seconds, the function finishes running, and we get a solution. We can check and see that the leaf's entropy is 0, and each possibility is represented by a leaf. So it is a valid solution as well. Let's visualize the tree. So there we go, we solved the puzzle. So, is that it? Well, why stop at 12 coins? Here's the solution for 11 coins, 8 coins, and 4 coins. What about the 13 coin thing from before? Right. So, as we mentioned before, we could ideally uncover log 27 bits of entropy. And because 13 coins have log 26 bits of hidden information, we could hypothetically find the odd coin out of 13 too. So let's find out if it is possible. We're going to run the code once again, but this time we set the number of coins to 13. And we almost found a valid solution. Just almost. Looking a bit deeper, we see that one leaf corresponds to 2 different possibilities, and these 2 possibilities are that one of the coins is either light or heavy. This means that with 13 coins to begin with, we actually do manage to identify the odd one, but we just didn't identify its relative weight. So what happened? Is our logic incorrect? Maybe there's a bug in the code? As it turns out, our logic is correct, and the code, while very inefficient, is still correct as well. After a quick search on Wikipedia, we find some formulas relating the number of weighings to the maximum number of coins. The case we need is the third one, where the relative weight is unknown and we need to identify it and the odd coin. There's also another case where we only need to identify the coin without knowing its relative weight. Subbing n equals 3, we get 13 coins. Notice that when we ran our code for the 13 coin case, our best result was exactly that, identifying the odd coin but without knowing its relative weight. That's nice and all, but how do they prove these formulas? Unfortunately, Wikipedia did not provide proof. But they did provide sources, which led me to this article by Cedric Smith that was posted on the Mathematical Gazette in 1947. Coincidentally, the logic he used to solve the puzzle was the exact same we used in our algorithm, which is really cool considering it was published almost 80 years ago. He then goes on to prove the general case, and while it is a very clever proof, it's quite confusing and the notation is, strange to say the least. It's definitely not something I could fit in this video, so I decided to look for another proof. After some further research, I found this article that was posted on the same journal 30 years later by Bennett Manville. This one's a lot less confusing, so I'll go with this one. We're gonna start with the simplest case where the relative weight of the coin is known. Here, it's not too difficult to show that given n weighings, you could identify the odd coin out of 3 to the n coins. We're gonna denote the maximum number of coins as k0 of n. As for the solution, you split all the coins into 3 equal sets. Let's say we know the odd coin is heavier than the rest. If the scale balances, then the odd coin is in the set that wasn't weighed. And if it didn't balance, the coin is in the heavier side of the scale. We can discard the rest and repeat this process until we're left with the odd coin. We found a solution with 3 to the n coins, so we know k0 of n can't be any lower than that. But also, since the initial entropy is at the maximum amount that we can uncover, we know k0 can't be any higher than that too. This leaves us with the only option that k0 of n equals 3 to the n. We can now make our problem a little more difficult. Each one of the coins can either be possibly light or possibly heavy, but not both. In this case, k0 is still 3 to the n. The initial entropy doesn't change, because there's still one option per coin. On top of that, the method of solution isn't modified too much. The only difference is that now, we make sure that both sides of the scale also have an equal amount of possibly light and possibly heavy coins in them. If the scale is balanced, then like in the easier case, we take the unweighted coins and discard the rest. Now, let's say the scales are unbalanced, and the left side is heavier than the right one. Of course, we can discard the coins that weren't weighed, which are a third of our coins. But we can also rule out 2 other sets. We can discard all the possibly heavy coins that were placed on the right side, because if any of them were actually heavy, the scale would have tilted the other way. And from the same logic, all the possibly light coins that were placed on the left side are also ruled out. Since we required both sides of the scale to have an equal number of possibly light and possibly heavy coins, these 2 sets would total to another third of our coins. That again would leave us with a third of what we started with. We can repeat this process n-1 more times, and there we go, found the odd coin. Let's complicate this a bit further. I swear we're almost there. Now we don't know the relative weight of the odd coin, but we're also provided with an extra reference coin that we know for sure is neutral. Here we're gonna add an r so we know that we have a reference. Now how do we find kr of n? If the scale balances, we discard the coins that were on the scale and keep the set that wasn't weighed. We know nothing about those coins, and we already used up a weighing. So to ensure we could solve the puzzle in that case, we must leave no more than kr of n-1 coins off the scale. If the scale doesn't balance, we discard the coins that were off the scale. But take a look at the coins that were on the scale. We know the coins on the light side are possibly light, and the ones on the heavy side are possibly heavy. And we already know how to deal with that case. If we want to solve the puzzle with the highest number of coins, the two sets on the scale must share 3 to the n-1 coins between them. But wait, you might ask. 3 to the n-1 is always odd, so how could we split this many coins to two equal sets? Well, just use the reference coin. Put one extra coin on one side and balance it with the reference coin on the other side. Adding up all these groups of coins, we get this recurrence relation, which we know how to solve. We can unravel the recursion until we're left with this sum plus kr of 0. With no weighings at all, it's impossible to determine whether even one coin is heavy or light. So kr0 must equal 0, leaving us just with the sum. This is a geometric sum that has a closed formula. It simplifies to this number. This number is also the same one that Wikipedia wrote for the second case, where we have no reference coin, but we don't have to determine the relative weight. It's no coincidence, but I'm gonna leave the explanation for y'all in the comments. By the way, according to information theory, this is the upper bound for determining an odd coin, because this time each coin has two options, so k coins have an initial entropy of log 2k. We could uncover at most n times log 3 bits, so rearranging, we get the number of coins is smaller or equal to 3 to the n over 2, and the highest integer that obeys this inequality is 3 to the n minus 1 all over 2. And now, we're finally ready to tackle our problem. We have k coins and n weighings. We don't know the relative weight and we don't have a reference coin. What's the highest k that we could solve the puzzle with? In other words, what's k of n? The solution here is kind of similar to the previous case. If the scale balances, we throw away all the ones that were on the scale, but learn nothing new about the ones off the scale. So we cannot leave more than k of n-1 coins aside. If the scale doesn't balance, we're left with a possibly light and possibly heavy set, which we already know can be solved with 3 to the n-1 coins. But because this time we don't have a reference coin and cannot split this many coins to two equal sets, we have no other choice but to make a concession and remove a coin. Again, we can just unravel the recurrence relation until we're left with this sum plus our base case k of 1. And for n equals 1, the information theory upper bound is just one coin. But even that's impossible because we have nothing to weigh our single coin against. This must mean that k of 1 equals 0. That leaves us with this sum, which could be simplified to a closed form expression. Wait a second. This doesn't seem right. The answer on Wikipedia didn't have this n-1 term. But it doesn't even matter what Wikipedia says, we already know it's wrong. If we set n equals 3, this would imply we wouldn't be able to solve the puzzle with more than 10 coins. But just a few minutes ago we showed it's possible with 12. So where do we mess up? You can pause the video for a few seconds to think, or maybe rewatch the last section if you want to. I'll wait. Okay, wait's over. Did you catch it? Let's go a bit further back. If the scales are balanced, we might not know anything about the coins off the scale, but we do have a secret weapon. Every coin that was put on the scale is neutral for sure, so any one of them could be used as a reference coin. We don't need to have just k of n-1, we could do just fine with kr of n-1. This little r changes everything, because we don't have to solve our recurrence relation anymore. We can just substitute the formula for kr, rearrange, and there we go, much better. This also agrees with the result we saw in Wikipedia, so that's also reassuring. Phew, that was a long proof, but we finally did it. But, you know, we've gone so far, so why stop here? Let's generalize just a bit more. One way you could make it way more difficult is by adding more odd coins. In a 2015 paper, Alexander Chudnov showed that it's possible to solve the puzzle with 11 coins, 5 weighings, and 2 odd coins with an unknown relative weight. They solved and generalized this puzzle using a field in mathematics known as coding theory, which also has many real-life applications, from the design of QR codes and memory devices, all the way to quantum computing. I really encourage you all to go down this rabbit hole yourself. We might explore this topic in another video. This is one of the most incredible things about these types of math puzzles. This puzzle is of course fun to think about, but its practical applications aren't so obvious. Unless of course you find a treasure chest with a fake coin. But on the road you go through to solve this puzzle, you might discover new ideas that have applications in unexpected places. So this is my wish for you all. Keep on learning and stay curious. You might find an actual treasure you didn't know existed.